Homework 2.6, Combinations of Functions, Video 1. Homework due Friday, May 22nd, 2020 at 11:59 p.m. You may have noticed that I've organized the board a little bit differently than the previous series of videos by putting the homework problems that you should try directly underneath here. And that frees up a little bit of space up in the corner. So in homework 2.6, by the time we finish this video and the next one, you should try questions 1 through 8. All right, so we're going to start talking about combinations of functions, but before we do, we need a little more clarity on the domain of a function. Now, I know we've talked about domain and range and stuff like that before when we talked about functions in general. But when you're talking about a function in function notation, and you're being asked what is its domain without being given a graph or a set of ordered pairs or a table, then the implication is you want the largest domain as possible. So we're going to define the domain of f of x as the set of all real numbers that make the function both defined and real. This part down here really isn't part of the definition, it's just a follow-up, so let's just put a gigantic green parentheses around it. So again, the domain of a function is going to be the set of all real numbers that make the function both defined and real. Now, what do I mean by defined and real? Well, let's think about what it means for a function to be undefined. There are a few things that make numbers undefined, or rather I should say some expressions that are undefined when done with certain numbers. But the one that's most common, the one that we know about at this stage, is don't ever have 0 in a denominator. So when we say defined, that means we want no denominators that are equal to 0. So if a function has a denominator, we need to make sure that it is not 0. Now as far as real as in not imaginary. So for real, we want to make sure that we don't run into any i's, into any imaginary numbers. So where did those come from? Square rooting negatives. So to keep the function real, we need to make sure we have no square roots of negatives. Now, within the realm of this homework, there are 3 types of domain issues. This video will cover the first 2, the next one will cover the third. The first type of domain issue is just regular polynomial functions, like f of x equals 3x plus 1, or g of x equals x to the 3rd power minus 3x squared plus x minus 3. There's a more rigorous definition of polynomial functions. When we get into chapter 3, that'll be after test 2. I'll give you that more strict definition of a polynomial function, but intuitively, it's just the sum and difference of whole number powers of x's, or whatever the variable is. Well, if you have a polynomial function, and the question is what's the domain, we need to avoid denominators being 0, and we need to avoid square roots of negatives. But these functions have no denominators that could accidentally be 0, and they have no square roots that could accidentally square root a negative number. So there's no way either of these issues could occur in a polynomial function. In other words, there are no numbers that are going to cause us trouble. You give me any number, I can put it into any polynomial function. I could put 5 here, I could put 19 here, I could put pi here, I could put the square root of 2 here, and I wouldn't get a denominator of 0 or a square root of a negative. So, when you're asked the domain of a function and it's a polynomial function, it's the easiest one. The domain is all real numbers. Or, if you want to write it in interval notation, open parentheses, negative infinity, comma infinity, close parentheses. So that's the easy one. No denominators, no square roots, no problems. Every number's in the domain. But for rational functions, which we technically haven't defined, but it's the word rational meaning ratio. A rational function, by definition, is a ratio of polynomial functions. So you put one polynomial on top of another. There are other rational functions where the numerator or denominator isn't necessarily a polynomial function. So for our purpose, we'll just say a rational function is a fraction with some function on top and some function on bottom. But if you have a function that is a fraction and hence has a denominator, then we need to be a little more concerned about finding the domain. because the domain requires that the function is defined and a fraction will be undefined if the denominator is 0. So what does that mean in terms of finding the domain? Well, the domain is all real numbers except solutions to denominator equals 0. In other words, we want all the numbers we can. So which ones do we not want? The ones that make the denominator equal to 0. So let's take a look at these three rational functions and see if we can find their domain. For this first function, we have 2x minus 5 in the denominator. We have 3x plus 1 in the numerator, but there are no restrictions on it. So to find the domain for this first function, we first have to figure out what makes the denominator equal to 0. Now, you could probably look at this and solve it without actually writing the steps, or even writing that equation. But x equals 5/2 would give us trouble because it would make the denominator equal to 0. So really, that's not our domain, that's what we need to avoid. So how do we avoid 5/2 and pick up every other number? Well, think of a number line where we put 5/2 in the middle because it's the number of concern, and we remove it. And we want everything else. So we shade in everything to the left, and we shade in everything to the right. Well, we just disconnected the number line into two disjoint intervals, two intervals that don't overlap. The left interval would be parentheses negative infinity, comma 5/2. Because we removed the 5/2, we wouldn't put a bracket, we would put a parentheses. The interval on the right is parentheses 5/2, comma infinity. And remember, when our solution is more than one interval, we can join them with a union symbol. This is a really weird way of saying everything except 5/2. All the way from negative infinity to positive infinity, but stop at 5/2, jump over it, and then continue. What about the second one? G of x equals 4x over x squared minus 9. I invite you to pause the video and see if you can find the numbers that make the denominator equal to 0. They're probably obvious. And see if you can write the domain. To find those numbers, we have to solve x squared minus 9 is equal to 0. Oh no, a quadratic equation. Well, you have options. You could solve it by factoring. You could really get out the quadratic formula if you wanted to. But because this only has a single x term, we can solve it pretty quickly using square roots. Add 9 to both sides and then square root both sides. Just don't forget to use the plus minus when you square root both sides of the equation. So these are the numbers that we want to avoid. So what would it look like if we took a number line and removed the negative 3 and removed the positive 3? Would it be partitioned into 2 intervals? Nope, 3 intervals. The first interval would start back at negative infinity, and I use the word start loosely. And the first number we would have to avoid is negative 3. So when we get to the negative 3, we would have to close that off, union, open up the next interval, which would start at negative 3, until we get to the next number to avoid, which would be positive 3. Close off that interval, union, and then open up the final interval, which resumes after 3, and then continues forever. So just think about the number line and removing the values that make the denominator equal to 0, and you can get the domain pretty easily. Let's take a look at one more, and this one's kind of a trick question. It is a rational function, and so as a consequence, we have to avoid the values, the real numbers that make the denominator equal to 0. Well, if we put x squared plus 1 equal to 0, we can solve it just like that one. Without much dilly-dallying, we can move the negative 1 and square root it. Don't forget the plus minus. Oh no, the square root of negative 1, that's, by definition, that's I. Well, our domain is a set of real numbers minus those, but those aren't even real. In other words, we can't do the same thing we did here. We can't get a real number line and remove I and negative I. You may remember where they live, one space above 0, one space below 0, but they're not real numbers, so they're not there for me to remove. So the domain would be all real numbers. The only numbers I needed to remove weren't even on the number line, the real number line. This one might also be pretty obvious, because if you square any real number, it'll probably come out positive. Adding 1 will keep it positive. The only exception is squaring 0. but adding 1 to it makes it positive. So finding the domain of a rational function boils down to solving the denominator equal to 0 and removing those numbers from the number line, and what's left is your domain.